Hey guys, so you've been working on those rectangle approximations, trying to figure out the area underneath or between the graph of a function and the x-axis. And we determined that those areas, when you calculate them, are called integrals. So the area between the graph and the x-axis is called an integral. You worked last time on finding definite integrals where you were actually given the area of the space between the graph and the x-axis, and you had to add those things together, or maybe you had to do a little bit of calculating on your own. But now we're going to kind of go forward and look at how to go from a function to something you can use to calculate the integral a little bit easier than adding up pieces. So we do that through something called antiderivatives. So we'll look at that in just a second. But I want to define two terms for you. One is a definite integral. That's what you all have been working with so far, where you're given a specific interval. If you can calculate the area of the space, you can get an exact amount. Those are those problems you did on Khan Academy last week. Indefinite integrals, you're not given a specific interval, so you can't actually get a specific answer. You can't get a specific area. So what you get when you do an indefinite integral is just sort of a general rule for that integral that you could potentially use if you had an interval that you could potentially use to calculate the definite integral. So we're going to look at indefinite integrals right now, and then over the next couple of days, we're going to look at some rules for finding antiderivatives and coming up with that expression for your integral, and then we'll look at how to use those to actually calculate out your definite integral. So those are my plans for this week. Is to cover all the rules of indefinite integrals between Monday and Wednesday, and then on Friday look at calculating definite integrals. So looking at antiderivatives, and y'all, you gotta excuse me because I've tried this like 3 times and I keep making mistakes, so I just crossed out my little typo there. But I want you to take a look at this question and then pause the video for a minute while you think about it. And come up with an answer. If f prime of x, so in other words, if the derivative of f of x equals 3x squared plus 2x, what is f of x? So what was your original function if you know the derivative? So pause the video for just a minute, think that through, and see what kind of answer you come up with. Okay, so thinking about how we calculate or how we come up with a derivative, what I get here is that f of x, that should not be there, f of x would have equaled x cubed plus x squared. Well, where does that come from? Well, if we were wanting to go from here up here, we would multiply by 2 and then reduce our exponent by 1. That would give us 2x. And then for this one, we would multiply by 3. There's the 3. And then we would reduce our exponent by 1. So that would give me 3x squared. So we're just working backwards. This is the antiderivative. It's working under the assumption that the function you're looking at is the derivative and you're trying to go back to the previous function. Okay, so there are a few rules associated with this that we need to look at. Some of them are pretty simple. The constant rule. The constant rule just says that if you are taking the derivative of a constant, and we always write dx because remember we're calculating area, and dx is the base of our subintervals as those subintervals get so small that they approach zero. So we're always taking the function and multiplying it times the base of our subinterval. But in this case, our subinterval is so tiny that instead of calling it delta x, we call it dx. So a constant, the interval of a constant dx, this is really an extension of how you would deal with any kind of exponent. Right now, this has no x on it whatsoever. So its x would have a zero exponent. So we would put an x on it. That x would have a invisible 1 as an exponent, and then we would divide by an invisible 1. But up here with this one, what would have happened if this original function had been like plus 5 or minus 7? What would have happened to those when we took the derivative? Well, they would have disappeared in the derivative. So we don't have any way of knowing when we do the antiderivative if there had been a constant in the previous function. So to reflect that, we always write plus c. And what that means is plus some constant. Now that constant could have been 0, but we just don't know, since when you take the derivative, a constant would have disappeared. So we always put a plus c. So let's look at this as an actual example, and let's do the integral of 4 dx. So what that 4 would become, like our a became ax, our 4 would become 4x, and then we always do plus c. So let's try one more. The integral of 7 dx becomes 7x and then plus c. Pretty simple, right? Okay, so the major rule is the power rule, or the reverse power rule. And I feel like most of these rules that I'm going to show you today, including the constant rule, really are variations on the power rule. So the power rule, the kind of general rule for that, is that the integral of x to the n power dx, so x to some exponent, is going to equal x to the n plus 1 power over n plus 1. Well, that's what we did up here, right? We took x to the second power, we did 2 plus 1 and gave it a 3 exponent. We divided by 3, which canceled out. Over here, we did the same thing. We took an invisible 1 exponent, we added 1 to it and got 2, divided by 2. And then, of course, plus c. So let's look at how that works out when your exponent is just 1. So we have the integral of x dx, knowing that there's an invisible 1 right here. So that would equal x to the 1 plus 1 power over 1 plus 1. So that equals x squared over 2. And then when we're done taking the antiderivative, we always add c. So this is, sometimes you'll see this as a unique rule, but it's not really a unique rule, it's part of the power rule. So another one you sometimes see as a unique rule is the integral of x squared. But this is just the same thing as the power rule. So this would be x to the 2 plus 1 over 2 plus 1. So that gives me x to the third power over 3. There's nothing to cancel, nothing to reduce, so I just leave the divided by 3 there. And then, of course, plus c. But it works the same way, even though sometimes people call these unique cases, it works the same. In fact, this one over here, our original one, let's say 7, let's go with this one. This is really an extension of the power rule, because another way to do, or to say 7 dx would be 7x to the 0 power dx, and that would just give us 7 times x plus 1, or x to the 0 plus 1 over 0 plus 1, and that just gives us 7x to the first power over 1, or just 7x plus c. See, same thing. It's just a variation on the power rule. Okay. All right, so let's do one more. So we'll say x to the 6th power dx. So that gives me x to the 6 plus 1 power over 6 plus 1. So that gives me x to the 7th power over 7 plus c. Power rule. All right, so the next rule is multiplication by a constant. And you actually do this, a similar rule when you do derivatives, but you're so accustomed to doing derivatives and just multiplying that you don't really pay attention to it anymore. And eventually you'll get that way with integrals too. But for right now, take it step by step if that's what you need to do. So what this rule says is that if we have a function multiplied by a constant and we're taking an integral, that is the same as pulling that constant out, doing the integral first, and then multiplying by the constant. Okay? So let's look at what that looks like in reality. So if we had 7x to the 4th power dx, another way we could write that would be 7 times the integral of x to the 4th power dx. And so you can write that as 7 times x to the 4 plus 1 power over 4 plus 1, or 7x to the 5th power over 5. And the 7 and the 5 don't cancel out, or they can't be reduced, so just say 7x to the 5th power over 5, and then of course we put plus c. So let's try one more of these. Let's do 4x dx. So we can pull that 4 out here to the outside. Of course, that's x to the 1st power. So we could rewrite that as 4 times x to the 1 plus 1 power over 1 plus 1. So I'm using, for each one of these things, I'm using my power rule. And so that gives me 4x squared over 2. But this time the 4 and the 2 reduce, so I can change that to a 2 and a 1. So that gives me 2x squared over 1, but I don't need that, plus c. Okay, so the last two are kind of related, so I'm going to do them as one set of rules. You'll see them as two different rules, but the sum and difference rules are related. And again, you do something like this with derivatives. So if we had, the sum rule says that if you wanted to take the integral of f of x plus g of x, another way you could write that would be the integral of f of x plus the integral of g of x. Okay, and that looks very complicated until you realize that what they mean is terms in a polynomial. So, for example, so this is the sum. So for example, let's say f of x was just 3x squared. And g of x was 2x. Okay, so we can rewrite that as the integral of 3x squared dx plus the integral of 2x dx. So for right now, until you get really good at this, and I'm telling you it's confusing for me, so take your time. I'm going to separate this out. I'm going to follow my multiplying by a constant rule, and I'm going to pull out that 3. And then I'm going to come over here. I'm going to pull out that 2. And I'm just going to do the integral of my variable. I'm not going to worry about the constants are outside now. So this would be 3 times x to the 2 plus 1 power over 2 plus 1. And this would be 2 times x to the 1 plus 1 power. I don't know why I was just going to underline that. Over 1 plus 1. And so this gives me 3x cubed over 3 plus 2x squared over 2. My 3's and my 2's reduce, and that gives me x cubed plus x squared, and then of course plus c. All right, so now we'll look at the difference. All right, so the difference rule, same thing. If you wanted to do the difference of the integral of the difference between f of x and g of x, you would take the integral of each thing individually and subtract. Okay, so let's say, for example, what I wanted to do was the integral of 6x squared minus 8x to the 4th power dx. So I could rewrite that as the integral of 6x squared dx minus the integral of 8x to the 4th power. And then once again, because even I have trouble with this and keeping my numbers straight, I'm going to pull my constants out to the side. And I am going to just take the integral of my variable. So this gives me 6x to the 2 plus 1 over 2 plus 1 minus 8 times x to the 4 plus 1 over 4 plus 1. And so this gives me 6x to the 3rd power over 3 minus 8 x to the 5th power over 5. The 6 and the 3, that reduces to 2 over 1. So I get 2x cubed. This does not reduce, so I'm left with 8x to the 5th power over 5. And then, of course, I have my plus c. Okay, so I left you all some practice problems to do for today. And then on Wednesday, we will look at a few other rules and then on Friday, we'll use those rules to calculate definite integrals, and that will take us through the rest of this week and into spring break. Oh my gosh. All right, I hope you guys are having some pretty good luck doing this stuff. You all have been doing really awesome for me. I hope you're doing as well for your other classes. If you have trouble with anything, please send me messages, and I will be posting times that I will be available to live chat with you, and hopefully be able to, I figured out how to use my cell phone as a document camera, so hopefully be able to even like live stream some work and all to help answer your questions and everything. But you all are doing great. I'm so proud of you. Keep up the good work. Bye, guys.